SMAW, also known as shielded metal arc welding. Some of you will be starting with shielded metal arc welding, probably not today, but within the very near future. So we're going to talk a little bit about this before we start on our safety test. So SMAW is also known as stick welding. Why is it known as stick welding? Because we like to stick the electrode a lot if it's not done properly. It is what is known as a manual arc welding process, okay? You physically weld, you physically change the electrodes. It uses what's called a consumable electrode, okay? So a consumable electrode means what? The rod is going to burn up and you're gonna have to replace it. A non-consumable electrode means that the rod is not going to burn up and be replaced. However, it is still considered a consumable. So just because it's non-consumable, it wears out over time, it burns up over time. But unlike a consumable electrode, non-consumable is designed to last long, a consumable is designed to be used up, right? So SMAW is widely used due to its simplicity and versatility. So you need to have either a generator or an electrical panel in order to power your power source, right? So you need a welder, an electrical panel or a generator, and then you need your electrodes and your leads. That is it, okay? Very, very simple. Not a lot of things that is required for stick welding. Unlike gas metal arc welding, to where you need to have the power source, you need to have the generator, you need to have shielding gas, you need to have wire, you need to have the correct drive rolls, you need to have the correct guides, you have to have the correct amperage and voltage settings and the wire speed settings. So there's a lot more involved with it. So that's why stick welding is very simple. You just need a couple of things, right? It's primarily used to join metals by creating a molten pole that solidifies into a strong joint. Okay, so let's look at the picture, for example. This right here is our base material, okay? As soon as we strike that arc, what happens? We complete a circuit. When we complete a circuit, we have a very hot flame. Right here is where we're completing the circuit, okay? And by completing the circuit, we're not sticking the rod onto the plate and holding it there, right? You're striking it just like you would, let's say, a battery terminal. Or if you saw a power line, you have the power line workers that will like connect the poles to the power line. You'll see a big arc come off of it before they connect it. That's the arc that we're forming, right? So what happens is we form our arc here, okay? Our consumable electrode, that's what this is right here, will melt. This burns somewhere between 6,000 and 10,000 degrees. Typically, you guys are burning about 6,500 degrees for stick welding, okay, or shielded metal arc welding. So this puddle right here is melting at about 6,500 degrees, right? We're taking our consumable electrode here, and we are melting it right here to where it's red, okay? That is called your weld, okay? The blue stuff on the outside of this is called your flux, okay? Flux coating is a bunch of different compositions that help protect the weld, okay? If I didn't have this flux on the end of this rod and I tried to weld, when you guys start physically stick welding, you will quickly realize that you need flux in order to establish a good weld. If you don't have flux, you're just going to continue to stick the rod onto the material and it's not going to weld, okay? So what happens is as soon as I strike this arc, that flux liquefies, turns into a shielding gas, okay? That shielding gas protects this liquefied weld and protects it as it cools, okay? Once it's cooled, if you look up here, the flux on your rod then turns into what's called slag, okay? Flux is good. You want to have flux. If you don't have flux, then you have bad welds. Slag is bad. Why is slag bad? Yes. So slag has caught all of the contaminants in the air, right? Any contaminant that might be on the base material, whether it be rust or paint or all of the things that are in the air, it catches all that and protects it. Protects the weld from pulling all of that stuff in, okay? So if we have slag on top of our weld and we don't remove it, and then we try to weld over top of that slag, now we're not going to melt that slag. It's gonna stay there. We're gonna cover it up, and then we're gonna have little voids in our weld, okay? So whenever we do the tensile test that we talked about yesterday, or like a brake test, or something along those lines, that's where the weld is going to start to fail, okay? Mr. Hughes used the example about a bridge, right? How it's constantly moving. If there is a spot to where an air gap is there, you can build up pressure, and then that's where your weld will start to fail. It'll crack from that spot, and it'll work its way either longitudinally or transversely along your weld, and then it's gonna destroy it, okay? So slag is bad, flux is good. You have to make sure that you remove all slag in your weld joints all the time, okay? You might, try to be lazy and say, well, I'm gonna cover it up, Mr. Spanik's not gonna see it. And I may not see it. But if you go out to the field, one of the things that, like bridges, for example, almost all bridges are 100% X-ray. So that means every weld that's made on that bridge is X-rayed, 100%. So if you try to cover it up to not let the inspector see it, it's gonna get X-rayed, it's gonna pop up, because you have to, every weld that you do in the field, usually you're assigned a welder's number, right? Mine was C41. That was my number when I was welding. So every weld that I did, I had to write in either soapstone or paint marker C41 right next to my weld, because then when it was X-rayed or inspected and it had to be repaired, they had to look up who C41 was, and then Derek Spanik had to come back and repair that weld. Okay? So just because nobody's there to see it doesn't mean you can cover it up, especially if it's 100% X-ray, because then it's gonna get uncovered. We have our workpiece, which, here's our welder, right? Where's current flow from? What terminal? Positive or negative?
Positive.
Negative. Work always flows from your negative terminal, okay? So your power comes out of your negative terminal, goes into your workpiece, and then as soon as you strike this arc, it goes into the electrode and then back to the power supply, okay? This is called direct current electrode positive. Your electrode is plugged into the positive terminal. Everybody understand that? Okay? If I wanted to flip these and put the plus on my workpiece, then it would be considered direct current electrode negative. Okay? So then the work would be flowing into your electrode holder, then into your workpiece. Okay? And then right here, this is all the shielding gas. This arc here and the shielding gas, this is all what you see. This is the bright light, the ultraviolet light that you see when you are welding. So SMAW has a rich history dating all the way back to the early 20th century. So we're talking back in the early 1920s, okay? It was developed for mainly a lot of shipbuilding processes. Oxy-fuel was around back then, but oxy-fuel welding, number one, doesn't give you enough penetration as opposed to stick welding, but also it's a very slow process. Has anyone ever seen oxy-fuel welding be done? Let's say like a 6-inch weld might take you 15 seconds, 20 seconds for stick welding. That same 6-inch weld might take you a minute or two for oxy-fuel welding. So it's a much, much slower process, very similar to that of TIG welding. It was very crucial, like I said, in shipbuilding, construction, manufacturing. This was all during World War II. What was happening during World War II? What were we building? All of the missiles, all of the tanks, everything that we needed for military, so we had to get all that stuff out of there quick, right? So we needed to make sure, number one, it was strong, and number two, that we had enough time to get all that stuff out of there. And then just like anything that's ever been generated before, there's always advancements in the electrodes and the equipments. So for example, the ESAW, everybody has heard of ESAW, correct? He's not very popular in the United States until, I'm gonna say, around 15 or so years ago. like over in other countries, very popular, but it didn't reach the United States until pretty recently. So a big brand in other countries, but primarily Lincoln and Miller were the big companies that were over here in the United States. So there's always advancements, always things going on. Feronius, for example, is a fairly new welding machine, and it's actually competing with all of the big expensive machines. So there's advancements coming along. All these inverters, they are getting smaller and more precise. The inverter welding machines. So definitely always advancements that are happening. So it operates on fundamental principles. Electric arc is created between the electrode and the base material. The heat generated by the arc melts the electrode at the base metal. Remember, that's burning at about 6,000 degrees Fahrenheit. So if you get your glove within 1.5 inches or 2 inches, it's going to take the leather on your glove and it's literally going to start melting it. That's how hot that arc burns. Now, if you're a couple feet away, obviously you're not going to feel the heat. You're going to get the reflection and the arc burns, but you're not going to feel that heat from being a few feet away. But if your face is in it and you're right next to it, you're going to be feeling the heat from that arc. The flux coating on the electrode shields the weld pool from the contamination, providing that protective gas and forming slag. Remember, slag is bad, flux is good. As the electrode melts, it deposits filler into the weld joint. Now, just like we talked yesterday about tensile strength, right? Let's say, for example, you're using a 7018 electrode. 7018 is a structural rod meant to hold things. The minimum yield strength for a 7018 electrode is 70,000 pounds per square inch, okay? If we have a really good weld, but it's full of porosity or slag, we are not getting that 70,000 pounds per square inch strength out of there, okay? So we've not met the requirements for that specific rod, okay? Usually, if it's executed correctly, it's like 10 or 15,000 more PSI as far as strength goes with that particular rod. So, we'll use an air compressor, for example, right? Air compressors, the one downstairs runs at about 150 pounds of pressure, right? So those welds are not tested at 150 pounds of pressure, right? They're tested at a much higher pressure. That tank might have been tested at 200 pounds of pressure or 250 pounds of pressure to the ASME boiler code, and made sure that they were strong enough to not break it and withstand the pressures there. So what do we need? We need our power source, right? It provides the electrical current necessary to create the arc. We have our electrode holder. Now, there are some electrode holders that may be worn out in need of replacement. If that is there and it doesn't hold your electrode, not a problem at all. Bring it to me, we'll change it out, and we'll have a brand new electrode. We don't change out electrodes very often, but we do change them out when they're bad and they don't hold your electrodes. So we have our ground clamp, which very rarely is that changed. It attaches to the base metal, or if you guys are working in the welding booths, as long as it's touching the table somewhere in the welding booth. There's usually brackets down at the bottom of the table where you can connect it right to the brackets. Really the only time that is needed to be moved, the ground clamps, is when you are working on a very particular project. Maybe if you're working on a V-groove or a certification test, when you're working inside of a joint, you get what's called arc flow. Arc flow is a magnetic disturbance in your weld. So instead of your puddle itself going into the base material and having that nice weld like you're used to, arc flow happens and it causes a magnetic disturbance, and just instead of your puddle going into the material, it kind of like bounces and like doesn't want to go into the material, okay? Everybody will experience arc flow. You'll know exactly what I'm talking about as soon as that does happen. And then our welding cables transmit the electrical current from the power source to the electrode holder and ground clamp. Remember, the farther we get our cables away from the machine, what happens? Go ahead.
The less amount of electricity.
Yeah, so the farther you are away, the less electricity that flows through there, which is called voltage drop, okay? So just like a power line, right? A power line can only go so far before it needs to have like a little boost, like a little pump that pushes it forward, right? So same thing with stick welding, except you're not gonna boost it, right? You're just gonna turn up your amperage a little bit, and by the time it gets there, let's say if you're delivering 120 amps at the welding machine, you might only be at 115 or 110 at the end of your cable per however long, 100 feet or whatever it is that you're running. All right, there are so many types of electrodes in welding, right? But primarily, we really only use a few, okay? Now, those electrodes will be specific to what you are doing, okay? So if you are a D1.5 structural welder, you're either going to be using the 7018 rod or E71T flux rod, okay? Those are designed for structural things, right? If you're a maintenance guy or a farmer, you're probably gonna be using something like a 6013 electrode, right? They're known as like general purpose electrodes. If you are somebody that works on a pipeline, right? You're either gonna be using 6010 as a root pass, and then there's a 7010 rod, there's an 8010 rod, which are the most common. You will use them for like your cover pass and your fill pass, or you're gonna use a 7018 rod over top of that. Or you might use MIG wire, E70S6 to run your root pass, or you might use TIG wire. But the main electrodes, 6010, 7018, 6013, are gonna be the most common ones. Now, 6010 is my personal favorite. It is a very deep penetrating electrode. It burns out paint, it burns out rust, anything dirty in the weld. That's why I like it. It has a very, very thin slag coating on top of that. So you can almost take the electrode out, flip it upside down, and scrape the weld, and that slag coating will come right off. Yes?
What kind of electrodes do you use for underwater?
That's a very good question. Zion here has an uncle who is an underwater welder, and we are working to try and get him to come in here and talk to you guys. So I think that would be an excellent question for him to talk to you about. I don't know anything about underwater welding to answer that question. So let's table that until we get somebody in here, and we'll find out. Yes.
First dad, he was an underwater welder, and he gave me a big welding book. Remind me something about that.
Oh, you want to bring it in?
Sure.
Okay. Bring it in. We'll take a look at it. Yep.
I found these like long, like orange rods in my locker.
Those are 7018 532nd rods. That's what those are. So then we have our E7018 rod. Now, each of these electrodes, they get broken down into either F1, 2, 3, or 4 group. That's called the F group classifications, and we'll get into that at a later time. But then we have an E7018, which is also known as a low hydrogen electrode. Produces high quality welds with good ductility. So remember, we were talking about the bridges, right? Very good ductility. Every time a truck goes across that bridge, what happens to it? It shakes, right? We don't want something that's very hard and that would break very easily, right? So we want something that's going to be real ductile, and 7018 is a good rod for that. Now 6013, it is known as like a maintenance rod, like I said, or a general purpose rod. One of the reasons is because it doesn't matter what welding machine that you have at your house, it'll weld on it. So you can use 6013 on all polarities, is what that means. So you can run it on AC, you can run on DC positive, you can run on DC negative. Whatever you do, it will work, okay? 6013 is kind of a mixture between a 6010 and a 7018 electrode, okay? It has the deep penetrating characteristics of a 6010 rod, but also has the nice smooth arc of a 7018 rod. So kind of a mixture of both of those. And it can be operated in all positions, which it doesn't operate in the vertical position as well as a 7018 or a 6013 rod. But it can be done, it's just the strength is not very good there. SMAW process advantages. So there are a lot of advantages to SMAW. There's also a lot of disadvantages to SMAW, but we're going to talk about the advantages right now. Number one is the portability. What is the portability? How easily it is to move around, right? So for example, you have your power source, your welder itself, and either a generator, well typically it's going to be a generator if it's being portable. Then you have your welding leads, and then you have the welder itself, right, and the electrodes. Very, very portable. Unlike, let's take gas metal arc welding for example, you have to have your welder, you have to have a shielding gas, you have to have a wire feeder, or it's a welder that has a wire feeder built into it. You have to bring like the wire rolls. So there's a lot more that goes with gas metal arc welding. Also, you don't want to use gas metal arc welding outside. You can, but you don't want to. Why? Because we lose shielding gas. So stick welding can weld a variety of metals in different positions. Now, there are some metals that it's not recommended for, like aluminum and stainless steel, but they do make aluminum welding rods, they do make stainless steel welding rods, and it can be done with it, but it's not going to be the best option, right? So if you're welding with aluminum, TIG welding is going to be the best option. If you're welding with stainless steel, TIG welding is probably going to be another best option for those, right? But you still, they make stick welding stainless steel rods, they make stick welding aluminum rods, so it still can be done, just not the most versatile. Very low cost. The initial investment is low compared to the other welding processes. I'm going to use gas metal arc welding again for a reference. I already told you about the stick welding and then the gas metal arc welding. Think about the cost. So not only do you have to buy a welder, you have to buy a wire feeder if the welder is not included. You have to either buy or rent your shielding gas. So just to put that into perspective, I have what's called a 139 cubic bottle. So it's only about this tall. And I bought mine for my shop, and it cost me to buy it and to fill it. It was about $350. That was just for the shielding gas. And that wasn't the large industrial tanks that you guys use downstairs. That was just this itty bitty little tank that's, you know, about yay tall. So that's about $350, okay? So it's a little bit more expensive. Now, you have to worry about buying wire, which you still have to buy stick electrodes, right? You have to buy wire. Then you have to make sure that you have the right size guides, and you have to make sure you have the right size drive rolls. Then you have to tote around this gas bottle, which all of that, you know, starts to add up as far as cost goes. And it's the most suitable for outdoor use. You know, MIG welding is really good indoors. MIG welding is really good for thin material. Stick welding is really good for outdoor usage. There are some limitations. The efficiency. If I was welding something for production work, right, and I want to get something done real quick and get it in, get it welded, get it out. Am I going to use a stick welding rod where I make a weld and then I chip off the slag and then I wire brush the slag and then I grab another piece and bring another piece in? Or am I going to use MIG welding or gas metal arc welding where I make my weld, I don't have to chip any slag off, make my weld, moving on, make a weld, moving on, right? So a lot less stoppage, a lot less post-weld cleanup with gas metal arc welding compared to stick welding. So the production goes down a little bit with stick welding. Also, if it's thin material, we'll use like shelving at Lowe's, for example, right? That is production work. If it's real thin material, now we have the chance that we're going to burn through that material. We're going to put too much heat into that material, and we're going to distort that material. It does require a skilled operator. So I can't say anybody can weld with gas metal arc welding, but it's a lot more difficult to stick weld or use shield metal arc welding than it is to use gas metal arc welding, right? And we'll talk about why on the next screen here. Now, for the most part, it is limited to ferrous materials, and it's primarily used on steels and casts, but they do make an aluminum stick rod, they do make stainless stick rods, they do make nickel electrodes, so it can be used on it, but that's not its primary focus, okay? Our heat ranges. Now, primarily, like I said, we use 60-10, we use 60-13, we use 70-18 in the shop. And out in the field, that's pretty much what is used for the most part, unless you're starting to get specialized, unless you're working on the pipeline. Then they have other rods. They have an 80-10 electrode, they have 90-18 electrodes. If you're doing a lot of welding in the flat or horizontal position, they have 70-24 electrodes, which are good for like high deposition. So let's use our 60-13 rod, for example. So we typically use 1/8 of an inch electrodes. 60-13, 1/8 of an inch. Operating range, these are just suggested ranges, are gonna be between 80 and 130 amps. Here, 1/2 inch plate, we're probably gonna be using about 115 to 125 amps with 60-13. You might look at Lincoln or Miller or Hobart or ESAB, and each one of those manufacturers is gonna have a different operating range for that specific rod. This chart was pulled off of Wiki, so this looks like a Miller chart, so that's probably what it is. So Lincoln might be 85 to 140 or 90 to 150, but those are all just suggested ranges. We're going to adjust the amperage based on the characteristics and weld pool behavior. So the 130 amps, if we're welding on 1/8 inch thick material, we don't want to be at 130 amps, right? We're probably going to we want to be closer to 80 amps, right? Too much heat is not good. What's the saying? More weld better? That sound right? More weld better? More weld is not always. More weld, more better is not always better, right? Thin material, we're distorting the material, we're burning through the material. So you have to make sure that your amperage reflects the thickness of material that you're welding on. So welding positions, 1G, 2G, 3G, and 4G. There's also 5G and 6G, but that pertains to pipe welding itself. So we have 1. What do you guys think the 1 is going to stand for? It tells you right next to it. It's the easiest, but what position is it? Which is what?
Above.
Huh?
It's from like above.
What's the position? 1G. Flat,
Flat?
right? So 1G is the easiest position, flat. So just because I say 1G, that doesn't really tell you guys much as far as 1G, right? G stands for groove, okay? So by looking at 1G, that's telling me that I'm gonna make a groove weld in the flat position. For example, up on the board, the top one, that is what a groove weld looks like, right? So if you see a 1G, when you guys get to welding 2, if you recall, Mr. Hughes was talking about putting a welding symbol up on the board, and that's your assignment for the day, right? You need to be able to, number 1, read a welding symbol and understand the terminology. So if he calls for a 1G and you make a fillet weld, you just made the complete incorrect weld, right? So you have to know what G stands for. So G stands for groove, which is just a single bevel on each piece, okay? The next thing we have is a 1F, okay? F stands for fillet weld. So just below the V groove, you'll see there's an example. The other thing that you guys have to worry about is travel speed, okay? So we have the arc length, that has to be 1/8 of an inch. The next thing is our travel speed. If I'm welding, let's say a 6-inch long piece, it shouldn't take me 10 seconds to get from the start to the finish, right? It should take me maybe 25 or 30 seconds, okay? If we have too fast of a travel speed, okay, our weld is gonna be real pointy, okay? You're gonna see that your weld is gonna be real pointy, and if we're welding really hot with that too fast of a travel speed, now we can get what's called undercut on the toes of our welds. That undercut is because we're going too fast and we're not giving that weld the opportunity to fill in, right, and create that weld. Our travel speed can be too slow. Remember, more weld the better is not always good. You know, we can put too much heat in, we can distort our material, we can crack our materials. And then our angle. I like to use the example of writing with a pen. I like to use the example of writing with a pen, okay? See this natural angle that I have here? This is about a 10 or 15 degree angle, okay? So there are two different types of angles that we can use. We can use what's called a drag travel angle, and we can use what's called a push travel angle, okay? So our drag travel angle, the end of our electrode is pointing at the beginning of the weld, okay? So if I'm starting here, I'm going this way, that's called a drag travel angle, okay? That's the one that we normally use. The only time that we'll use a push travel angle, which is pointing towards the end of the weld, not the beginning of the weld, is if we're working out of position and we want to push that weld up because we're working against gravity now, okay? So for the most part, drag travel angle, okay? Push travel angle is usually only done in the vertical position. All right, so what type of defects can we get? You guys already know about porosity. Some of you have already experienced porosity in your welds. So there's itty bitty little pinholes that happen. A lot of times porosity can happen from dirty materials. Porosity can happen from when you restart your electrode. You're tapping it, right? And then your flux falls off. And now you have your bare wire. Now you have no protection over your filler. And then you get porosity into your weld because it's contaminated. You also have slag inclusions. That's where you make your weld and then you don't get rid of all your slag. Slag's trapped underneath of there. Then you make another weld over top of that. And just like Mr. Hughes was talking about the bridge, right? All of that movement starts to build up pressure. Pressure in that little void is going to eventually cause a crack and cause a failure. Crack can be caused by excessive stress or improper cooling rates. So the most common type of cracking is going to be like longitudinal cracks, transverse cracks, and that's going to be happening mostly on cast iron materials. That's where you're going to see it the most. Cast iron is not very ductile. It doesn't move very easily. So it has to have pre-weld or pre-heating treatment done onto it, and then you weld it, and then it has to have post-weld treatment done onto that. And if it's done improperly, if it cools too rapidly, it pulls all that together, and then we have cracks in our welds. Yes?
Are we gonna be doing any cast iron welding?
Probably not. The next thing we have is our undercut, which we've talked about. Undercut, it happens on the toes of your welds, and it can happen for multiple reasons. Well, your weld being too hot, being too far away from your material, going a little bit too fast, right? So all of those things come into play when we're making our welds. Bunch of different applications. We have construction, which is what you're in, manufacturing, automotive, maintenance and repair. And each one of these areas is going to have probably a different type of welding or a different welding rod involved with it, right? Construction might be a lot of stick welding. Manufacturing might be a lot of MIG welding or flux core welding. Automotive is going to be probably a lot of MIG welding, not necessarily flux core because it's thin gauge material. And then maintenance and repair is probably going to go back to the stick welding, maybe with those 6013 rods that we talked about. Couple of takeaways. Getting good at shielded metal arc welding and understanding it is, it takes a lot of time, it takes a lot of patience, it takes a lot of practice. So if you're going into a welding booth and you're just standing there playing on your phone and playing Clash of Clans and whatever other games you're playing, it's not helping you become a better welder, right? It's not helping you. Welding requires a lot of practice. If you're not practicing, if you're not repeating, you're not getting any better. And you're just hurting yourself, right? It's your grades, it's your project, and it's your time. So if you're wasting all of those, then you're not going to get any better at welding. And that goes for anything in life. You know, the NFL players, they don't just wake up on Sunday and go play football and then go back to the couch for the rest of the week, right? They go to practice, they run their plays, they do repetitions, they do the same thing every week to get better at it. You know, the Olympics, the World Championships, those wrestlers aren't just showing up and wrestling, right? You have to go, you have to practice, you have to repeat yourself. Next thing is the proper technique and attention to detail, okay? If you have a bad weld, fix the bad weld. If you have slag trapped, fix the slag entrapment, grind it out, repair it. Don't be lazy and just weld over top of it. It might pass for now, but if you're used to that, it's not gonna pass in the future, especially when we get to X-ray type of things, and bend test types of things. And then continuous practice and training are key to developing proficiency in sheet metal arc welding.